Good morning. Welcome to Humpkey's Study once again. I've got something different to show you this morning when we start off. You know, occasionally living in the country, occasionally people just drop off things. Sometimes it's old beer cans, sometimes it's animals. And yesterday, somebody dropped off an animal at our mailbox, and our postman brought him in. Yeah, tell him about it. Well, I'll show him about it. So the postman brought in Quill. Quill, it's okay. It's okay. Quill is about a 2-month-old porcupine, and you have to be a little careful if he spikes you. But he's gotten around now, and he was a little cold when he came in, but he's feeling good now. Yeah, he's really cute too. So this is a new menagerie, and I guess thanks to the people that dropped off Quill at our house, he gets along with Ohm too. He's kind of slow. I kind of like him. Yeah, I Ohm. But anyway, we've got now an extra creature living around here. So occasionally he'll make an appearance. Quill, I think, will make an appearance even on this makeup exam coming in. So what I'd like you to do today there have been some comments about the chickens too. How are the chickens? They are doing well. They're doing very well, actually. So today I'd like to talk about this max-min problem. I'd like to kind of put some closure on it today a little bit. And to do this, I'd like you to open the document. It's a Mathematica document called I Got This, and it's to go along with this video. So if you haven't downloaded it, maybe pause this video and download it, and then take a look. So I'm going to share the screen right now with that and explain what's going on with it. There we go. So here is this document. This is how to find the max-min stuff that I'm going to ask with Mathematica, when it works, what it doesn't. I put up here in this first area up here, I put in a given function and I put in a given triangle. I gave the triangle as part of the plot packages. And so I think these are going to be all the commands that you would actually need for the vast majority of questions that I will ask. So what kind of things are we interested in? What's the setup? The setup is that we are given a function, say of 2, or we might have 3 variables. And we want to take a look at this thing, first of all, plot it as best we can. If it's a function of 3 variables, we'll only have contour plot to look at. But if it's a function of 2 variables, we can actually look at the graph. The graph lies in 3 dimensions. We'll also want to find the global local extrema and analyze them. Are these local maxes, local mins, or inflection points? We won't succeed completely, but we'll do pretty well. And then we'll want to restrict this function to a given region and find the max and mins, all the stuff we've been doing. So there are a couple of plotting commands here. We can plot the graph, and I have the plot command filled in here. So what we're looking at here is kind of a max-min template. Well, that came up pretty quick. So here I've plotted the domain. The domain is a triangle, that's in blue. And then the graph itself is in yellow. So the graph, some is positive, some is negative, and that's what she looks like. We can also look at a contour plot just over this triangle. So here is a plot over the triangle. So the triangle that you see here is the blue triangle above. And the one contour that you see here between dark gold and light gold is exactly the 0. And you can see this when you hover over it. It says 0 on there, or should if you hover over it with your mouse. So this is the contour plot. And this is kind of heat. So blue is colder or lower, negative in this case, and the lighter colors are higher. You could color this in various ways. I like rainbow in particular, but here are the two plotting things that we can see. And we can see from this directly that the maxes and mins are likely at, this is likely a max and this is likely a min just from the contour plot. We can see the same thing from the graph. This is the high point here and the low point is down there of the graph. So these should occur at the corner points. So let's talk about locating and analyzing local maxa and minima for this function over this region. So these are called global, not because they're everywhere, but they're everywhere for this function. And this function includes its domain. And in this case, the domain is a triangle. So a function is not just an equation. It's an equation together with a domain, and that's what we've got here. So these are the things that you might do. Find the derivative of f, which will be a vector quantity, set it equal to 0 and solve. This will give you the critical points. The critical points are the ones that have horizontal tangent surfaces. Horizontal in this case is relative to the x, y, z axes. The x and y are our domain. Z is the height. So these are the ones that have tangent planes whose equations are z equals constant. The tangent, the graph is, I'm making motions like a graph here. You guys can't see this. But anyway, the tangent at a maximum is a plane that is tangent to the graph, but just lies above it. It'll be horizontal. Z equals the maximum value. At a minimum, the tangent plane will be z equals, I don't know, -10. That's the minimum value. And at saddle points, it won't lie above or below the graph, but the graph will pierce it, but it will still have a horizontal tangent surface there, tangent plane. So how do we do this? How do we do this process? This is the nsolve command. You're going to take the derivative, that's derf. You set it equal to 0, that's double equal to 0. And now we numerically solve. If we just do solve, it'll use algebraic exact methods. And that can be really complicated since you can't solve, there is no algorithm that solves even polynomials for fifth degree and above. So here we go. We only have one critical point for this function. The equation has several, but there's only one that lies inside our domain, so refers to our function, and it's the point 0.807573. The y value is 0.794 approximately. Now we're going to look at the Hessian. The Hessian is the determinant of the second derivative. One of the things I'll ask you to do by hand is find the first and second derivatives of these functions. The Hessian is the second derivative, so in this case it's a 2x2 matrix. Its determinant then is computed above where I computed Hess F. So Hess F gives you the Hessian, and if we plug in that point, and you plug in the critical point, 0.8076.794, plug it in, and we'll see what we get. I get -605.262. Well, it's the negative that really counts here, because that negative for a Hessian tells you that you have mixed concavity here. In some directions, the graph is concave up, so it looks like a minimum. In some directions, the graph is concave down, looks like a maximum. This thing is a saddle point. And so in number 2, the directions say, compute the Hessian at each of these critical values to determine consistency of concavity. That's what the Hessian tells you. If the Hessian is positive, it tells you have consistent concavity there. If the Hessian is negative, it tells you you have inconsistent concavity. If you have inconsistent concavity, that's a saddle point. If you have 0 for the Hessian, that actually means the test doesn't tell you anything. You'll have to look at other methods. We won't. We'll talk about this maybe later, but doing the basics here, our Hessians will either be positive or negative. So if the Hessian is positive, it would be consistent concavity, and you'd have to check if it's a maximum or minimum. And you only have to check one direction, because if you know that the concavity is consistent, then one direction will give you the same concavity as any other one. They might vary in amounts, but they'll all be up or they'll all be down, all be positive or all be negative. So we'll check the second derivative in the direction x. In the direction x, then the graph is just a curve, so you're looking at a calculus kind of thing. So we'll look at the second derivative of f in the x direction, and we'll evaluate at the point x equals a and y equals b. In this case, we don't have anything to evaluate because the Hessian was negative. But if we did, we would. And let's get down to that. And if we do, we get minus 10 minus 10a squared plus 20b squared. So that's what we would get in the case that you would use part 3, but you only use part 3 in 1 out of 3 cases. This gives you a fairly complete look at the local maxima and minima of the function f, the equation in the region. Locating the global maxes and minimas, that's what we did on the homework for yesterday, or for Monday. Finding the global maxima and minima of these real valued functions over a region. So what this amounts to is doing part A, finding the global critical values that lie inside R, and then checking on each of the edges. And you check on each of the edges by parameterizing the edge. For a straight line edge, you just parameterize fairly straightforwardly. It's just the straight line, and if you do it in kind of the most straightforward way between 2 points, is t will be between 0 and 1. And so you check for critical points of that one variable function. It will just be, t will be your only variable. Find the critical points, check the endpoints, do that for each portion of the edge. It's a lot of work, but this is the way it goes, and we're going to do it with the maximize command. So I am going to uncomment out maximize. Maximize does what you do. As far as I know, this is secret, but since these are exact values, it can't differ very much from what I just told you. So it does exactly what you did on that homework last night. And when you do this, you find that the maximum is 76 and occurs at 0.22, which is one of the vertices of the triangle. Now, if you use n maximize, so I'll comment out maximize and use n maximize. What n maximize does is it floods the triangle T with billions of points, and then checks the values at each one and keeps only the top one, and does it until your accuracy is correct. Now, actually, it's far more sophisticated than that, but I wanted to point out that in some sense, this is a brute force approach to finding the maximum. But if you specify an accuracy that's even like 8 decimal places, this is pretty effective with today's technology. So if we do it, we get the exact same answer. So maximize and n maximize are different. And you can use either one to do this. If you don't get an answer from maximize, which can happen, then use the end maximize. I'm interested here in the values that we get. I'd like to know about what this looks like. We don't really have to know the exact value. And minimize is the same. So here the minimum of the function is minus 198 and occurs again at one of the vertices, 0, 3. So this is the template that I'd like us to use. These are the kind of questions that I will ask you about maxima and minima. One of the questions I'd like to ask you about is finding a tangent plane at a critical value. That's easy, should involve no work, so be careful of that question. And so that's about it. So thanks a lot. And Quill has had his very first lesson in multivariable calculus. Says he didn't get a thing, but I hope you got something out of it. And see you tomorrow.